So I'm not sure if the title fits, but we will see during the lectures. And I'm going to talk on one main project and then give overview of the others. Just a list of collaborators and funding. So I'm going to show some metal oxide work that I do with Aryeh Zaban, Ohad Levy, and Stefano Cortarolo. And the people that work on it are Mifsam, Alon, and Alon. Materials and processes for energy storage, which I'm not going to talk much. And those are the people that work on. Graphene doping, which actually started when I was in NU, and I will just mention. And light matter interaction, transport, and real space TT DFT code development that I also started in NU and now do some collaboration with Manish Jain and also people from here. Okay, so with metal oxides, I'm first going to talk about prediction of Raman, where we try to compare Raman calculations to experiment, and you will see it's a quite useful tool. Do some calculations of several oxides, and then talk about data-driven structure prediction. So first of all, why metal oxides for photovoltaics? They are very abundant cheap materials, cheap production process, very stable materials, and they also allow many different combinations. The problem is that it's hard to find materials that have both the band gap and the proper conductivities, and so it's difficult to produce such materials. In recent years, there are the perovskite rush, so there are new technologies in photovoltaics, so it's interesting, and this is some motivation. So in this talk, I'm using a guiding example where my experimental collaborators mixed magnesia and copper oxide, and they got in the mixture also some photoactive material, which they were not sure about its properties. And so we tried to see whether there could be some compounds that are a result of this mixture, where this material is with a gap in the solar range, and this material is a transparent material with a very high band gap. And since there is the ICSD, we will soon see that there is one answer. But just about copper oxide, you see experimental band gap reported between 1.3 and actually 1.7. And there are many different calculations, even last year, that predict different results. And this is a very not esoteric material. Now, the material is anti-ferromagnetic, and its Néel temperature is at around 213 Kelvin, which I will go back later. Now, when we looked for compounds, we found that such a compound exists and, in fact, was found in the 70s. The band gap the experiment found was 1 eV. We actually found much higher band gaps. And also, when we look in theoretical prediction of formation, we see that it's metastable in the range of tens of milli-electron volts. So, but still it exists in experiment. And this is now under preparation. Now, in the group of Aryeh, they try to characterize materials by Raman measurements. So basically, they mix two materials with pulse laser deposition in a way that creates a gradient where on one side you have one material and on the other side you have the other material. And in the middle, you have a gradient of compositions And so, depending on growing conditions and annealing, you could hope that some crystalline structure might form in the middle. And then they do many types of robotic characterization. And one of them is Raman. And a powerful technique is a technique that does self-similarity. Basically, it compares different Raman spectra to each other, and it decides that this part is more similar to itself than this part, than this part. And so you could hope to build maps of material properties in a completely automatic way, and then repeat this for Raman, XRD, and other measurements. And basically, we were hoping to compare, to do some analysis, theoretical analysis of Raman properties for those materials. So just what happens with Raman spectroscopy, we know that we shine light, and then from the difference of the photons, we get the vibrational energy and get the Raman shift. And so basically, we probe vibrational properties. In theory, we can calculate the vibration properties by having the derivative of energy with respect to the ions. And this would basically give us the spring constant between atoms, and so the frequencies. Now, this is not enough. If we want to somehow say something about Raman intensities, one can go and try to calculate the differential of polarizability with respect to the normal mode. And so using this, you can see this is a work of my student Alon Kukliansky. You can see that this is actually experiment, and this is a theoretical prediction where the width of those lines is mostly by Gaussian broadening, so I would not really be sure about the width, but the ratio of intensities is related to the change of response of electrical properties with the mode. And you can see, for example, that for this material is a very good fit. This is calcite. Now, when we look at copper oxide, this doesn't look like a very good fit, but first I should stretch this because this goes till 700, but we still have those 3 peaks. And we have also one smaller peak that I will get into later, almost not noticed. And you can see that if we go to another phase of copper oxide, then we get a quite different picture. And for example, in this comparison, we would say that this is more similar to this, and this is more similar to this. Well, at least I would say that. So, and so initially we were interested to make discrimination between different phases of copper oxide and the copper-magnesium possible compound. But at some point we become interested in this peak, which is only copper oxide. And so something that is important in those materials is that we have spin arrangement that can be, since it's an anti-ferromagnetic material, the spin configuration can be at a larger crystal cell than the original cell. And this is important because if you don't model the correct spin, you can get wrong electronic properties and also wrong other properties. And in some cases, in this material with wrong spin configuration, you will get also wrong structure, and in a significant way. So I will not get into many details, but the thing we found is that when we take the correct spin configuration, we find this peak. And this peak is a peak that is found below the nil temperature. Now, if we take wrong spin configurations, we don't find this peak. So this peak disappears and is completely spin dependent. Now, it should be mentioned that whenever you go to bigger cells because of magnetic symmetry, the thing that happens is that if you just calculate vibrations, you will have phonon folding into the smaller Brillouin zone. And so you will see more gamma point phonons. And then you must do the analysis whether those modes are active or not, because otherwise we can take simply a much bigger cell and we will have many more vibrations, simply because of the fact that we took a bigger cell. And of course, if our calculation was dependent on the cell size, then there would be no way to trust it. And in fact, one of the things we test with the Raman estimation is that indeed we take bigger cells and we get the same Raman spectrum. So here we got this peak simply because of symmetry breaking that is happening, true symmetry breaking that is not artificial and is happening because of the specific spin configuration. And this work is currently under preparation. Now, if I go back to the original problem, then you can see that the copper, magnesium, and actually this is the copper, magnesium, and this is the Cu4O3. Are not very far, and we're still trying to check whether we can easily compare between them and find a specific peak that will tell us that we have this compound and not the other. So just to summarize, this is a really powerful tool, and it can also reveal some interesting modes that are spin-dependent. One problem is that in perfect crystals, some peaks are not allowed, and in actual experiment, because of grain size, they become allowed, and then it's very useful to calculate the full phonon spectrum. In many materials, there is two-phonon Raman scattering, and this is difficult. Well, more difficult is underestimation of the concept. It's very difficult to calculate. And this is not a rare phenomena. And in addition, in magnetic materials, we have also spin waves, which are also not simple to calculate like magnons. And actually, in the group of ARIA, they see such peak for nickel oxide, where this material has a nil temperature that is above room temperature. So they have the spin arrangement at room temperature. So the next question we ask ourselves is whether there are additional phases of this material, and experiment tell that there is such a phase with 3 coppers, and but the ICST does not have such entries. And so Osvaldo already showed in the morning structure comparison. And this is a known graph for silicon, where they compared different hypothetical structures by theory and got that silicon gets the lower structure. Today, we could do a structure prediction with essentially the same concept. There are codes that do evolutionary algorithms. And also, recently, there are codes that do what is called random structure search. And basically, I'm going to talk more about this. So initially, we played with OSPEC, and I must say that OSPEC does evolutionary algorithms. Here I started with a random guess and got this structure, and it works for many materials. It takes lots of time, and also it needs sometimes some help, but you many times can get to a correct crystalline structure. We now try to build a different concept, and this concept is basically related to the older concept of data finding using different possibilities of structures, where we simply collect all the ternary oxides that are known. In this graph, we look at AX, BY, OZ, and you see here A, B, O, and this should be symmetric, so I don't draw this line. And basically, this says how many compounds are there in ICST that are A1, B1, O3. So this, and the bigger the circle means there are more compounds. So, for example, here there are like 400 compounds that are simply A1, B1, O3. And another thing you can see is that you have much more oxide-rich materials than oxide-poor materials. So if you're searching for an oxide-poor material, you will be in some trouble with this method. But our idea is that we find the leading structure prototype and then use them as template for new materials. For example, we can take the diamond structure, which we get from carbon, and test it for silicon. Okay, and here we do it on a much larger scale. We simply collect many possible structures and use them for as a template for possible structure relaxation for DFT calculations. And with this, we got back to this problem, and we actually managed to find a structure that is lower in energy than USPEC for this system. It is still positive in energy, so it's still metastable. So this, obviously, this mixing of copper and magnesium is not the best system to check, but and it's not saying that USPEC is bad. Actually, I think evolutionary algorithms can find, but maybe I did not run it in the best way. This run, however, was much faster because I simply used enough data prototypes, and it was really fast. Finally, in those systems, we want to also optimize the spin, because most systems do not have neutron scattering data, so we need to guess the spin information. And basically, the idea is also, as Baldo mentioned, is to build Heisenberg-like models, and basically we can imagine such a flow where we calculate several anti-ferromagnetic possibilities. We find the J's, and then we search more structures with the simple Hamiltonians to find the lowest state energy, and then use Monte Carlo or known formulas to predict Néel and Curie temperatures. And you can see, for example, for nickel oxide, that with single first neighbor, we don't find a very good fit. But when we go to second neighbor, this is density functional theory, and this is a really simple Heisenberg model for the energy. Now, it is interesting to note that this is actually not new. Many people have done this. But the performance of such Heisenberg models is not the same over different materials. And by the performance itself, you can learn something on the material. Because With some materials, it's enough to have a second neighbor. With some materials, you must have a third neighbor, and so on. And clearly, when you need too many neighbors, you don't have enough data points, and so your model might be not really that good. And this is something we are now consistently checking for several materials. Okay, so I will skip the graphene, although it's with NU. I will show, actually, I will just say that we do some simulations of graphene and graphene doping. We do modeling of processes and materials for energy. And here in this project, we did Poisson-Boltzmann modeling. We now get into molecular dynamics modeling. This is too noisy, but we actually want to get some properties of polyelectrolyte liquids for batteries, and then go to higher level models. What I find is that in many problems, it's not enough to be here. This is a very nice sketch of Guy Makov from Ben Gurion. It's not enough to stay here, but we need also some insight from here and sometimes from here, especially for phenomena at surfaces and some other processes that we want to study. So we invest also time here. Another project that we do is organic, inorganic, actually this is all organic interface. And here we have a system where we found with Roy Yerushalmi a very simple electrostatic model, where the electrostatic model gives very good fit to experiment. But most reviewers wanted us to also do DFT, and DFT is not really easy for this system. Actually, it's quite complicated, and I will not get into this, but there are a lot of issues of getting correct hydrogen bonds, and also the fact that you can have many different configurations of the molecule above the surface. So in this case, I prefer electrostatic models on DFT, but finally, I do also time-dependent simulations and development. One for nonlinear effects with small molecules. This is actually H2+, so this is Schrödinger and not time-dependent DFT. We develop real-time time-dependent DFT in solid and surfaces, which work is done by Eldad Yahel in collaboration with Stefan Kummel. We develop grid-based Poisson solvers. This is in collaboration with Amir Bog. And now we develop also Hartree-Fock in real space for molecules and solids. And this is done by Nick Bofi, who is sitting here. And he's a Fulbright student that is coming from NU. And this is done also in collaboration with Manish Jain from India. Thanks. Yep.
I apologize for the question. Probably it's not for you.
Yep.
But I ask because I know nothing about this field. And
Yep.
When you mix two materials,
Yep.
only two, the question what you'll get out depends on the initial miscibility.
Yes, and also.
You can get either continuous alloys or space separation or total separation depending on the immiscibility. But my question is, what happens when you mix two oxides?
So.
It's clear that you do not get two different phases and just mixture of two different.
So it really depends on such graphs when you mix one material and the other. So let's go for the very simple situation where you find that you mix A and B and there is a compound, And I'm talking about the thermodynamically stable phase and not the kinetics. There is a compound.
My question is,
Yeah.
if you mix just copper and Ju and magnesium,
Yeah.
they're miscible. So if they're not miscible, why does one expect to
Why do you say they are not?
because the formation enthalpy is positive?
Yes, but this is because this graph. Yeah. What I'm trying to say is that we calculate those graphs to know in advance whether we could expect such a material or not. Now, our calculations show that this material is a bit with positive energy formation, so it should separate two parts. But still, the interesting thing is that it was formed by experiment and got crystalline structure characterized and even spin data characterized. So my guess is that under certain conditions, this metastability becomes stable. Now, there is also, if you read carefully the experimental data, you see that this copper-magnesium mix might be not completely pure. So this might stabilize, because you're right that if the formation enthalpy is positive, it should separate. Yeah.
What are the properties of the mix?
So then it's a completely different question. Yeah. But we are mostly interested in those mixtures that become stable. Yep.
I had a different question. So is Raman mode that appears around 250
Yeah. Yep.
Right. Do you know how it affects the exchange interactions? Do you know the physical vibration mode?
Yes, actually, yes. We can actually see that it's related to two opposite spin coppers that move with respect to one another. Yep.
Can you show the next diagram? Just a quick comment about this question. Where you have this spec thing.
Yeah.
Yeah. So just a quick comment. If you look at the right-hand side, the final best result is that the mixture has higher energy than the endpoint.
So
that's the definition of phase separation. And that means thermodynamically, as you of course well know, that at any finite temperature, you can stabilize only the alloy, but never the ordered phase. So there is no ordered phase according to that, if you take that seriously.
but still, there is a puzzle because we find it to be not not stable, but experiment does find this.
For a second, you forget experiment because we don't know exactly if it's single phase or multi-phase. This one says very clearly it cannot be an ordered phase.
Yeah.
That's it. But I'm very interested in what you said, the very exciting question of how many oxides there are of ABO in this triangle.
Yep.
So can you tell us a little bit about what's the current answer to the question, how many oxides there are?
Actually, it is on my computer, but I don't have the answer, so I don't want.
Magnitude, what, 1,000, 10,000, 100,000?
It's order of thousands to 10,000.
These are only oxides with negative formation energy.
Those are oxides from ICST. It's not.
The experimental ones.
Yes, it's not.
I thought this
No, because we first pull the data from ICSD to find all the stable one, and I would not commit on the number because I need to check.
Very, very quick question. You've shown about the spin configuration affect the Raman.
Yep.
Is it because the Raman is sensitive to spin configuration, or is it because spin configuration stabilizes different structure, and different structure naturally have different Raman?
We actually checked this, and it's not. We actually took the other spin configuration structure with the other spin configuration and ruled that out.
In other words,
So,
it's the same structure.
So if we take the same structure with the different spin configuration, you don't get this peak.
Oh, I see. So in other words, the spin configuration affects structure.
Yeah.
And structure is reflected in Raman, not so.
No. This is not what I said. Spin configurations affect structure, yes. But when we check the structure of both the correct spin configuration and the wrong spin configuration with the wrong spin, they all do not show this peak. So it's definitely an issue of the spin and not of the structure. And so it makes it interesting because this is one of the things you want to check. Yeah. Yep. Yep.
So related to this ABO, this
Yep.
space,
Yep.
how many structures do you think we don't know that exist with the oxide?
It's a good question that I don't know to answer. But my guess is that some people already have this answer because some people have done similar analysis. And you can see already from the example I showed that there are many compounds that will not be formed. So there are not that many. There is, I think, in a work from the group of CEDAR that I can send you.
Yeah, we can talk.
Yep.